Okay, so before we conclude the chapter about blowups, there's one more nice application that I want to mention, namely that by blowing up, we can take these rational maps that we have started with, and sometimes we can make them into actual morphisms by taking a blow up of the domain of this rational map. And to give like one of the very basic examples, let's look at a particular rational map. So if X is any affine variety and you have R functions on X, then we can define a rational map to the projective space PR minus 1 by sending X to this, this vector here in homogeneous coordinates given by F1 of X up to FR of X. So this these kind of things we have seen before already, and there we noted that this is a well-defined map as long as this vector is non-zero. In other words, as long as we're on u equals to x minus the vanishing locus of all these functions. And in general, you can check in examples. So for example, when x is just a affine space AR and the Fi are the coordinate functions, then this cannot be extended further. You cannot go over this set here. It's just, and the problem is that there it really depends on how you approach this set, what your limit point in this FR minus 1 is. Intuitively, this already shows that you cannot really extend it over this point in a continuous way. And however, we can still kind of get an extension if we're willing to modify the domain of this map. So here downstairs, we have just this rational map F from X to PR minus 1. And then if you recall, how did we define the blowup? Well, we defined the blowup by taking the map F on U. This is a map from U to PR minus 1. And its graph then sits inside U cross PR minus 1. So the graph of F sits inside U cross PR minus 1, and in particular inside X cross PR minus 1. And then we defined the X tilde to be the closure of this graph. So the blowup was defined by the closure operation. And then, well, we of course, from the blowup, this sits inside there, we can just take the projection to the second factor and get back to PR minus 1. So we do get a map from the blowup to PR minus 1. And then we just observe that this blowup, because, well, if you start with something, let's say for simplicity, if X was irreducible, then U is a dense open subset, then this is a birational map. And moreover, this diagram here commutes because somehow on the locus where this map here is defined, U, then we saw there's an isomorphism from U to its graph. And then if you take the projection to the second factor, then this exactly gives you the map F. So somehow this diagram here commutes as a diagram of rational maps. And so, so this means that we started with this rational map, we replaced the domain by a birational variety, X tilde, and then this composition here is then actually can be extended to all of X tilde, is actually given by a morphism. And so this is then sometimes called resolving the indeterminacy, because this was a map which was not determined everywhere, has some indeterminacy, and by blowing up, we could resolve this indeterminacy because this now has a map everywhere defined. Okay, and the final example, which is first of all a very concrete example, and second of all appears a bit later and will be used when we discuss the lines on the conic surface, is a very concrete one that we actually started with, sort of. Namely, we had seen that P1 cross P1 and P2 are birational. Seeing this is actually not difficult because somehow both of them contain A2 as a dense open subset, and we saw this is already enough to be birational. And in fact, what we can do here is we can write down an explicit birational map between them, and then resolve the indeterminacy of this map and of its inverse, actually. And here, for this, I'm just going to describe the construction. We're not going to see so much of the details of the proofs, but you'll see the references. So somehow, if you want to write down this birational map, we can actually combine two constructions which we have seen before. The first is that for these products of projective spaces, if you recall, we had the Segre embedding, which somehow recorded for all the coordinates here and here, recorded all their pairwise products. So since somehow this has two coordinates, this has two coordinates, we have four pairwise products. So somehow the Segre embedding lands inside P3, and it records these four coordinates. And we saw that the image of the Segre embedding is actually projective variety, and we wrote down some equations describing it. And then I think it was maybe an exercise that in this case, the equations are very simple. They boil down to a single quadratic equation, which is this x0, x3 is equal to x1, x2. So this was one way to see that this product P1 cross P1 is actually just a quadric hypersurface inside P3. Okay, so here we started with the thing we're interested in, and we wrote it first of all as this hypersurface. And then when we had this hypersurface in projective space, there was a second construction, which was the projection from a point. So we had, when you have a hypersurface, you have a point on there, and you have some complementary hyperplane, and you can take this projection operation, and this lands in a complementary hyperplane for this single point. So this lands in a P2 inside P3. And in this case, we project from a very particular point, namely from this point 0, 0, 0, 1. This is a point in X, right? Because if you plug in x0, x1, x2 equals to 0, and x3 equals to 1, then the equation is satisfied. So this is a point in X. We project from this. And actually for a projection from such a coordinate point, the projection is very easy because you basically take this coordinate and just forget the last coordinate. Okay. And this is a fine thing. And so we did manage to start with P1 cross P1 and end in P2. But the problem is, of course, the projection operation is not defined when you are exactly at the projection point. This we have also seen. We can also see this from this recipe that we wrote down because, well, if you plug in this, if you try to plug in this point here, then you would get the point 0, 0, 0. This is not well defined. Okay, so a priori, we just get some rational map from here to there. And you could check, if you write down some coordinates explicitly, you could check that this is in fact a birational map. So this would already give us something like this. And then the question is, can we resolve the indeterminacy maybe by blowing up some point in here? And the claim is this is possible. And in fact, I mean, somehow P1 cross P1 is the same as X. So basically we start with X, a rational map to P2. And we saw the unique point where it's not defined is this point A here. And then we take inspiration from the things that we did above. And then we hope that maybe if you blow up the point A, then this composition here is actually extends to a morphism. And this turns out to be correct. So if you blow up the single point of indeterminacy, then this rational map can actually be extended to a full morphism from this blow up to P2. And this is then still a birational morphism now. And then you can ask, what about the inverse map? Because birational, we can also go the other way. So somehow we do get a rational map from here to there. And this also has 2 points of indeterminacy, namely B and C, like this, these two coordinate points in P2. And then the great thing is if you also blow up these points, then also the inverse map becomes a morphism. And then you actually get morphisms in both directions, which are inverse to each other. And this shows then, so somehow once you do all these proofs and you check all these things, this shows that you started with this birational map and you made it into an isomorphism by blowing up one point in P1 cross P1, and sorry, this should be 1, and 2 points inside P2. Okay. In particular, this gives us an interesting relation between varieties, namely P1 cross P1 and P2 were not isomorphic, but if you blow up 1 point in P1 cross P1 and 2 points in P2, then you get isomorphic varieties. And that's an interesting thing, and that will be kind of used in 2 chapters. Okay. And so what I did here was I just kind of described the story, how it works. And so if you want to have more details, there's kind of 2 different proofs, and they're both given in Gatman's script, but I'm not going to discuss the details here. The first proof is a very explicit calculation with coordinates. So basically, you can imagine when you do these blowups, you have all kinds of local charts. You define them by some equations, and then you can basically just look at what does this map F do in equations, and then show, well, both this map and its inverse then make sense after you do all these blowups. This is the style of proof here. And then there's also this kind of geometric interpretation via projection from A that I started here, and then Gatman explains a bit more of these details, how you check that after the blowups, these maps are well defined. And so, as I said, I'm not going to give the details here because it's not so important, but I think that in general, this idea of starting with rational maps and then blowing up their indeterminacy to get some well-defined morphisms, this is a really important thing in many parts of algebraic geometry. Okay, this was the last video about blowups. And then in the next video, we're going to talk about the nice local properties of varieties called smoothness and singularities of varieties.